All right. All right. So I'm willing to answer some more accounting problems, but not today. Before we leave this first chapter, we have two more sections in chapter 1. I want to move forward. Just remember, we're going to be counting things for a long time, so you'll still get practice with things. And so before we leave this chapter, I'll go back and answer some more questions. I might even bring up some more counting problems on my own. But I would like to talk about the last two sections out of this chapter probably between today and Monday, right? And it has to do, so we're at 1.5, conditional probability. In some ways, this is still, right, I mentioned last time, or one of the last times, you do get, in probability, you get a lot of things thrown at you pretty quickly in the first 2 weeks, but then we spend 12 weeks trying to organize it and make sense out of all of it. Sort of the nature of the beast, because probability is, it's either new to people, or they think they know, I mean, some people might legitimately know some probability, but they kind of think they know some probability and realize, have to realize very quickly that there's a lot more to know. So let me give it a table, so conditional probability. I'm going to use the example out of the book. It's a good table. Let's see. So D plus and D minus. T plus, T minus. If you have your book, this is on page 16. If you don't, no problem. 25, 14, 18, and 78. Okay. So there's a table for us, and let's look at context. So these researchers conducted a study of the relation of the concentration of digitalis in the blood to digitalis intoxication in 135 patients, and then we have these things. So D is going to be some disease, represent some disease, and that disease plus is either present or it is not present. Okay. T is going to correspond to some particular test that is available, and that test either gives a positive result for the disease being present or a negative result for the disease being present. So just think about it this way, right? We have this population, and in this population, there is this disease, right? Some people have it, D plus, some people do not have it, D minus. Okay. Now there is a test to try to determine who has this disease. It all seems very timely, right? There's this T plus, right, which would say, yes, this person has the disease, and there's this T minus, which would say, no, this person does not have the disease. And as we can see from this table, they don't line up exactly, right? In a perfect world with a perfect test, your positive test result would be all here and none here, right? This is what we would call a false positive, these 14 people, where they do not have the disease, yet the test says they do, right? That would be the false positive stage. Just the nature of the beast. It's hard to determine whether or not people have certain things. It doesn't matter if it's digitalis, intoxication, or coronavirus, or certain types of cancer, or whatever it ends up being. Right? And then again, with a perfect test, in a perfect world, if your test result says negative, that you do not have it, you would hope that this number here would be 0, right? Which would correspond to people with the disease that get a negative test result, right? That's what we would call a false negative. Okay. You get a negative on your test result, even though you actually have that disease. Okay. And then, of course, this would be a true false, true negative, and then this one would be a true positive. Okay. So you get a positive when it says you have a positive. So think about it, again, this way. Venn diagrams are always very nice ways to think about these things. So let me think about, let's say inside of this circle would be the D plus, right? The people with the disease, are represented by the inside of that circle, which means the people without the disease are represented by the outside of that circle. And then, of course, test results, right? Let's say positive test result, T plus, right, is inside of this orange circle, and then, of course, a negative test result would be outside of that circle, right? In a perfect world with a perfect test, those two circles should overlap, right? Should be perfectly, and not just overlap, but they should be the same circle. Of course, that's not what happens, right? We have people that are inside the positive for the disease, but outside the positive for test, right? So here's our false negative, right? And then let's see, these are the outside. This one over here is outside the positive, or sorry, inside the positive for the test, but outside the positive for the disease, right? So these would be our false positives, right? Right, and with a perfect test, you would like these two values to be as small as possible, and ideally, you would like the white and the orange circle to overlap perfectly. But again, it doesn't happen pretty much ever. but it doesn't happen very often. I don't know of any perfect tests out there. Okay, right, so that's the idea. So tables like this are very informative, right? We can do a couple of things here. We can get our total values. I'll just complete this table. Again, if I start doing arithmetic in my head, then I'll start getting tired, so I'm just so 39, right, would be the total number of people who test positive, and 96 would be the total number of people who test negative. Vertically, right, we could add 43 is the total number of people with the disease, and 92 is the total number of people out of this population that does not have the disease. Okay. And then if I either add vertically or horizontally, or if I just add these four numbers here, I get the 135 people that were part of the test. Right. And if I wanted to, I could certainly, right, I could fill those numbers in here, right? Each of those numbers correspond to how many are in these different regions. So inside D plus and T plus, there'd be 25 in here. Let's see, T plus and D minus, right? 14 over here. D plus and T minus would be 18 over here, and D minus and T minus would be 78 out here, right? That's how many fit into each one of these categories. Okay, right. And so we can answer certain questions, right? We could take these results here, which is just some study taken from a larger population, right? And we could translate it into probabilities. Just using this population. D plus T minus, or sorry, D minus T plus T minus. Okay. And how would I do that? Well, I could get a number like 0.185, 0.104, 0.133, and 0.578. And that would be translating these numbers here, right? Knowing that there were, 135 total people in the population, right? Those would correspond to, okay, I have this population of people, 135 people. I'm gonna put them in a bag, shake them up, and draw one out at random, right? Don't quite do that. I'll put the names instead of them in the bag, right? Put their names in a bag, shake them up, and draw them out at random. And this is saying 18.5% of the time, I expect to draw a name that's in this region. 10.4% of the time, I would expect to draw a name in this region. 13.3% of the time, I would expect to draw a name in this region. And 57.8% of the time, I would expect to draw a name in this region. Okay? So what am I doing? I'm just taking each of these numbers here and dividing by the total. And we can do the same thing we did over here. Let me keep that in orange. Why not, right? Total, right, in the same way, I could add these numbers here and I get something like 289. I could add those numbers there, I get something like 0.711. I could add those numbers there, I get something like 318. Add those numbers, 0.682, right? Add those numbers or those numbers there, and I get a 1, which I usually wouldn't write down. Okay. And again, it's telling me sort of a similar thing for the groups, right? That is, put the names in a bag, draw one out. 28.9% of the time, I should get someone who tests positive, without regard to whether or not they have the disease, right? 71.1% of the time, I should get somebody outside of test positive, right, which would be outside of this circle. So these numbers correspond to what's happening in these little, each little distinct region. These numbers are corresponding to what's happening in this circle, outside of this circle, and the same thing over here, inside of this circle or outside of that circle. Right? So that's the idea. And where are we going with all of this? Well, because sometimes we'll have this population and we will know certain things about this population. Sometimes it's just one thing, sometimes it's two things, right? And a question ultimately could be, well, how well, I have these two different events, how well do they correspond or correlate to each other, right? Here I would prefer perfect correlation, right? I would prefer every time I knew somebody was in this group, I knew they were also in this group, right? I would prefer, ideally, if I knew they were in this group, I knew they were in this group, okay? And sometimes it's easier to get, figure out if they're in this group as compared to this group. Maybe sometimes it's easier, right, to figure out the other way, but typically not, right? And I'd like to be able to say things like, knowing this extra information, right? Knowing this extra information such as they had a positive test, okay? I could ask the question, well, what is the probability that they actually have the disease versus not have the disease? Okay. Again, right, we pick up a newspaper, you can read about all kinds of false positives or false negatives within different tests. COVID-19, right, coronavirus type tests is the big one these days, but it doesn't matter at different times, right? And so we'd like to understand the correlation, or we'd like to understand something like, given this information, okay, I'm no longer just looking at the big population, now I'm only interested in what's happening with the positive tests. What is the probability that this person actually has it versus not having it? Right? Given this information about a person's age, what is the probability that this is going to seriously affect them versus be something potentially less serious? Given the fact that somebody has kidney issues or diabetes, but it's oftentimes comorbidity, right? Given the extra information, does it allow us to say something about a disease versus a not a disease, or a serious reaction to it versus a not so serious reaction to it? Okay, right. So that's the idea here. Given information about something that's not the particular event, but somehow it seems like it might be related, what can we say about the other thing? Okay, so we can already do certain things like the probability, a handful of them. If I wanted to know the probability of T plus intersect D plus, okay, what is the probability at random I select someone who has a positive test and actually has a disease? That's this region in here, and that's what this number here is telling me, what 185. And that's different than what we're going to write in terms of conditional probability, which would be D plus, straight line here, T plus. So this is a particular region within our Venn diagram, and this is going to ask for something. This is our first conditional probability. We would read this one as given, right? Given I know the person had a positive test, right? What is the probability they have the disease? Knowing that there is not a perfect correlation between these two things, right? There's not a perfect one-to-one matchup. That sometimes we get these false positives, and sometimes we get these false negatives. And so, it's just very simply, what it does is, instead of looking at the entire population here, right, the given, by the way, the given is always on the right-hand side here, and then the probability that we're trying to calculate is on the left-hand side. Okay. So the probability of B plus is really just asking, what's the probability that when we draw a name out of the hat, they're in that circle right there. And that's what the probability of B plus would be asking for. Okay. The probability of B plus given T plus is now saying, okay, the first question was saying, let's take the entire sample space, the entire rectangle right there, and figure out the probability of B plus, and it includes and is exclusively this entire circle right there. Okay. What this one is now asking is, okay, I'm no longer interested in the entire population. I have extra information, right? I'm actually only interested in that part of the population that corresponds to T plus. So I'm now going to, let's just say, reduce my sample space not down to T plus, right? Meaning, now I'm only interested not in the entire rectangle anymore. In fact, I don't want to erase it, but I could just erase everything outside of this circle. And I'll say, okay, I have this extra information. I know this person is T plus inside of here. Now I'm just going to ask the same question. What is the probability that this person, right, is also in D plus? Okay. Which is now asking the question, right, inside of this circle, what's the probability of being in here, inside of the circle, which is going to be the D plus side of the circle, versus, you know, in some sense, versus over here, which is going to be the D minus part of the circle. Okay. And the answer will be what? Well, it's going to end up being, go back to white, right? There are 25 people over here compared to, now, my new sample space is T plus, compared to the 25 plus 14 people that were in that T plus category. 25 over 39, and do I have a decimal approximation for that? Sure. Approximately 0.640. That's rounded. So about 64% approximately. And by the way, how do we calculate that? We calculate it by taking the number of things, a number of results that were in D plus and T plus, and we divide it by the number of things in T plus. Again, we learned not so long ago, you know, if I want to compute the probability of A and everything is equally likely, we're going to have to move away from this assumption sooner or later. It's not going to take long. We're going to be there very soon. Everything equally likely in the sample space, all the results of the sample space equally, all the outcomes of the sample space equally likely, then I can take the number of things in the sample space, right, in the denominator, and the number of ways A occurs, and I can compute probabilities in that way. And again, if everything in the sample space is equally likely, and since I put names on slips of paper, I'm going to assume I'm equally likely to pick any one name as any other name, right? Then I've reduced my sample space. I'm no longer looking at the entire sample space, but I've restricted it down to just the T plus, everything inside of that one circle. And so now I'm not interested in just D plus in general, but only those D pluses that are inside of that circle. And so I could do it that way. So I could calculate it that way. And by the way, I could divide by the number of things in the big sample space here, and I could divide by the number of things in the big sample space here if I really wanted to, which would tell me the probability of D plus intersect T plus divided by the probability of T plus, right, would be a way to calculate it. Right, we will use this interchangeably, right? Sometimes we'll talk about the number of ways certain things can happen and calculate it that way. Sometimes we'll talk about, more often than not, we'll talk about probabilities. So it's saying instead of using 25 and 25 plus 24 for the numerator and the denominator respectively, I could have used 0.185 and 0.185 plus 0.04 as my, am I on the right side? No, 0.185 and then 0.185, 0.133 as my numerator, and then the sum of those as being my denominator respectively, right? But the sum of those two things is also down here. So again, in terms of a probability, I'll say, well, I do T plus, oh, come on, I have to get the right side here. T plus, right? Sorry, I was right with the horizontal to begin with, right? So the first question was, given the entire sample space, right, that's that one, what's the probability? And now the question is, if I restrict myself only to the T plus here with those numbers there, what is the probability? And the answer could also be calculated as this number divided by that number, right? That's our new number. Or this number divided by the sum of those two numbers. So this would be the probability of true positives, right? Whereas if we ask for what's the probability of D plus given T minus, right? The situation where the test result I know is going to be a negative, but I actually have the disease, which is what I would call a false negative. T minus now says, I'm going to restrict myself to everything outside of this circle, right? Now this time, I'm interested not in the entire sample space, but only what's happening in this group right here. And the answer is, I'll just write it in terms of the probabilities, 0.133 divided by 0.711. The D pluses occur here in terms of the probability of the whole, and the total of a T minus here would be 0.71. And then that number should be, approximately 0.187. And again, we could have used these numbers, right? It would have been this number divided by the sum, or x divided by that. And those would be our false negatives. And then, let's just go with one more, D minus given T plus, right? That would be our false positive. And so here, I would be looking at T plus again, what's the probability of being here? That would be our 0.104 divided by 0.289. Oh, I don't even have that number here. But what is that going to be? I guess I can pull out a calculator here. Someone has it, they can shout it out. 4 divided by 0.289. 0.33, sorry, 3599, about 36%. Of the time I get a positive result, the actual result is not having the disease, right? False negative, right? About 18.75% of the time I get a negative result, I actually have the disease. So again, this is the context here is this. We have a probability question that we want to answer. We can ask, what is the probability of this happening? And then, what is conditional probability? Well, I give myself extra information. Now, does that extra information lead me to update that probability? Right? I could flip a coin 3 times. I could flip 3 coins in front of me behind a screen. And then I could say, well, what's the probability that there's at least 2 heads? Okay. And then I could take and I could move one of those outside and I could show you, well, there's a head. Now what's the probability there's at least 2 heads out of that, right? So now you have this new information. You know, it could be that new information doesn't tell you anything new in terms of what you knew. That's the next section. That's called independence. Or it could be that new information that, I just showed you that there was a head there, somehow makes you want to update that probability, right? Update what your prior belief is with the new posterior belief. Okay. So think of conditional probability. You give yourself new information, test result. Can you update the likelihood that certain things are going to happen? Okay. All right. So, give ourselves a couple of definitions. So I'll just repeat. So here's our definition of conditional probability. Let A and B be 2 events with the probability B not equal to 0, right? So B is not impossible. Right? It's not impossible for B to occur. Okay. Okay. The conditional probability of A given B is defined to be, so our given is always, we put this vertical line in the middle of it. Our given is always on the right-hand side of it. Our thing we're trying to compute the probability of is on the left-hand side of it. Okay. Is just the case where we restrict our sample space from omega with everything occurring down to just B. So our new sample space is now just B. And then the numerator would be the results of event A occurring and B, right? Those things in A that were also in our new restricted sample space B. We could also use n's here, right? If I knew that this situation occurred where the number of things in the sample space were all, the things in the sample space were all equally likely, this is a much more general result here, the one we're going to use more often. Okay. But if everything's equally likely, we could rewrite this as n of A intersect B divided by n of B. Okay. Right. So again, just really think about it as instead of just looking at the entire sample space, sigma, we're now just going to restrict it to B. And instead of thinking of the probability of A occurring in the entire sample space, sigma, we're going to think about what about just those things in A here that are also in B. Okay. Right. So that's our formula. That we can calculate those. We can calculate those all day. We're actually going to use this as a tool for calculating some new probabilities. And so let's see. We have something called the multiplication law, and then we'll do an example. Multiplication law. Okay. Which says, start the same. Let A and B be events with the probability B not equal to 0, right? Why? Well, we don't want to divide by 0, that's undefined. Right? With the probability B not equal to 0, then it says, essentially, I can rearrange this equation right here, and I can calculate the probability of A intersect B as So multiply both sides by the probability of B. The probability of B multiplied by the probability of A given. Okay. And so what this is going to allow us to do immediately is allow us to calculate more complicated probabilities using this idea of conditional probabilities. Just a simple, right? We couldn't do this before, we can do it now. Here's an experiment. Let's see, I have this coin, and I know the probability of heads on this coin is 0.6, right? It's not a fair coin. Every time we've done this so far, we've had to work with a fair coin. Okay. Why? Because with a fair coin, then I would be equally likely to get heads or tails, and so then I'd be in this situation where everything in my sample space is equally likely. Okay? Or if I were to flip that coin multiple times, I would still, since every flip I'm equally likely to get the heads or the tails, then I would have a sample space even when I have head, tail, head, tail as the outcomes if I flipped it twice. Everything's equally likely, and I could calculate, those probabilities there. So now let's just say I have this coin. Probability of getting heads on that is 0.6, and the probability of getting tails on that coin is 0.4. And then I could ask the question is, what is the probability of flipping heads on both? Of course, if I flip twice. And actually, maybe I could have figured that out. Certainly I could have figured it out, but I didn't actually have a way of answering that question before, because I know if I were to write out the sample space, I still knew that what could happen. I could get head, tail, head, tail. But because it wasn't a fair coin, those things aren't equally likely. It certainly isn't 1/4. So now what could I do? Well, let's just ask it this way. I flip a coin twice. What is the probability I get heads on the first flip? I'll call it H1. And I get heads on the second flip. And what this multiplication law is telling me is that it will be the probability I get a heads on the first flip multiplied by the probability I get a heads on the second flip, given I get heads on the first flip. And so again, it allows me to take this more complicated probability question, which wasn't that complicated yet, right? But they'll get more complicated. But it's more complicated in that I have to flip this unfair coin multiple times and turn it into two different experiments. What's the probability of getting heads, and then what's the probability of getting tails after I got that head? Or sorry, heads after I got heads. Yes?
This might be a stupid question.
No stupid questions.
When it comes to the probability of H2 given H1,
Yep.
isn't that still a problem? Because to find that, we have to go back to the probability of the intersection between H1 and H2.
So let's think about this. Okay, so first of all, what is the probability if I flip this coin? What is the probability I get heads in the first flip? 0.6. Okay. Now, I'm going to pick the coin back up, and I'm going to flip it again. What's the probability of getting a heads on this now second flip? 0.6. And what's the justification for it being 0.6?
The first flip doesn't impact the probability of the second one.
Yeah, actually the first, if it's the same coin, if I believe this statement that, right, every time I flip the coin, this is what's going to happen, then it's independent. By the way, this is the idea of independence. I'm using independence without ever defining independence, but A and B are independent if the probability of B given A is the probability, right? B, right? That given this extra information about what happened before doesn't impact the probability. That is actually the idea of independence, and we'll talk on Monday about that. Appendix, right? Right? And so I'm making the assumption that, and it's a fair assumption because that's sort of how I think about coins, right? That when I take that coin and flip it the second time, you know, it didn't get a little dust here or there that somehow changes the weighting a little bit, right? That there's nothing new, and that this is just going to be the probability of H2. Now you're right, if it's not independent, right, then it would be a problem. We'd have something to calculate here. But we're going to assume that the result of the first flip doesn't impact the second flip, right? We're going to assume independence without ever defining it, right? And we're going to go from there. Okay. So then the probability of getting heads on the first flip and heads on the second flip would be 0.6 in terms of squared, right? Which would be 0.36. That would happen 36% of the time. Okay. As opposed to when that coin was fair, occurring a quarter of the time or 25% of the time. Okay. Yes. So just say in general, we have to be very careful because sometimes new information allows us to update, right? It changes this probability here. In this case, it does not. And actually, oftentimes it will not, but not every time. Sometimes it will. So we'll have a whole, if you go ahead after this class and you can read through the next section, which is 1.6 on independence, and it's really just on this idea of when does having new information not allow us or not require us to update our probabilities of what would occur. Okay. So there you go. So it was just this multiplication law, right, with this conditional probability that now allows it in thinking through this idea of the second flip not being affected by the first flip, that allowed us to calculate now a more complicated probability question. I mean, it wasn't an incredibly complicated one, and maybe it turned out exactly as I thought it should. Oh yeah, 60% chance on the first one, 60% chance on the second one, right? 0.6, 0.6, 36% chance that they both end up that way. I mean, it's not earth-shattering, and maybe everyone would have guessed if I would have asked the question to begin with. But now we've grounded it in at least some sort of reasoning. All right. So let's look at another one. So I'm going to have a bag full of balls that are all red or blue. So there's 3 red and 1 blue ball in this bag. I'm going to draw 2. We could answer this in another way, but we're going to use conditional probability for this, or this multiplication law. 2 balls from the bag. And we'll ask the question, what's the probability? The first one is red and the second one is red. Now, we could use combinations and we could count the number of things in the sample space, but we'll use this multiplication law, which says, okay, let's figure out what the probability, when I pull the ball out of that bag, it's red, and we'll multiply it by the probability when I pull a ball out of that bag, it's the second one, it's blue, given the first one was red. Right? And now, this is going to be important, right? Because if the first one was blue, then that would change this probability compared to that first one being red, compared to never drawing one out to begin with. By the way, the book writes down this formula with these 2 things flipped around. I like it better this way because it's more instructive in terms of in order, right? I could say, if I wrote it the way the book sort of writes the initial formula, then the probability of R1 intersect R2 would be the probability of R2 given R1 times the probability of R1, right? which really has you starting at the end and working your way forward, right? Where it really makes sense to say, okay, tell me the probability that the first one was red, if I write it this way, and then now that I know the first one was red, tell me the probability that the second one's going to be red. As opposed to looking at it this way, okay, given that the first one is red, what's the probability the second one is red? Okay, now tell me what's the probability the first one's red, right? I mean, it just switches the order, but this is certainly, if I think about these things as sequential, which I oftentimes will do, then it lets me to say, okay, this is the first thing that happened, and now this is the thing that happened as a consequence of that first thing happening. So just to point out, when the book writes this, it writes these two things in the opposite order. I don't know why, it doesn't make sense. Because then when the author uses it in an example later on, then he'll write it this way. And then later on, when he writes it in general again, he writes it in this order again. I don't know why. It's certainly much easier to think about it as, okay, this happened as a result of that. Or something else happened, and then, you know, what happened as a result of that, right? Where things we're going to add some other things that'll happen later on. Okay? All right. So I just wanted to point that out. It gives us a nice sequential first thing, second thing, first thing, second thing going through here. Okay, so what's the probability I draw a red ball out of there? Where there's 3 red balls, 1 blue ball, so when I draw a ball out, the probability it's red is? Yeah, 3/4. No trick questions here. Not yet. We can come up with trick questions later on. And then I multiply by, okay, now that I drew a red ball out and did not replace it, the composition of my bag is 2 red and 1 blue. Now what is the probability that I draw a red ball out of there? 2/3. Right. And then I 4 it. Okay, I should have been able to do that also with combinations, but it just gives me another way to look at this. Let's see. Okay. We got that formula. Okay. Let's go with more, right? So here's an example. Ooh. We'll make it fancy now. So now I have 2 bags with balls in them, right? This one has 3 red and 1 blue. And then this one has 1 red, let's just say 2 red and 2 blue. So again, I'm going to, now this time my experiment is, I'm going to grab one of the bags, I'm not going to look into it, okay? So I'm going to select a bag at random and draw a ball. And then I would ask the question, what's the probability that the ball I select out is red? Well, maybe I'll ask this question first. What is the probability that I select bag 1 and the ball I select out of it is red? Maybe that's a better first question. Okay. And the answer would be, what's the probability that I select bag 1? And then, what's the probability I select the red ball out, if I draw 1, given that I selected bag 1? And if I select a bag at random, what would we attach to the probability of selecting each bag? 1/2. 1/2. I mean, if it's really equally likely, the probability of selecting one of the two, right, either one of the two would be 1/2. And then, given that I selected, here's my bag 1 and here's my bag 2, what's the probability of selecting a red ball out of bag 1? 3/4. Right. So the probability, right, so this is my experiment. I have these 2 bags in front of me, they look identical. I can't tell anything from the outside of the bag. I grab one of them, I put my hand in, I pull out a ball, and what's the probability that after I've completed that experiment, I picked up bag A, or bag 1, and then I drew a red ball out of it, and the answer was 3/8. Whereas I could ask the question, what's the probability I select bag 2 and a red ball would be the probability of bag 2, and then the probability that I would select a red, given that I selected bag 2. So again, the probability I select bag 2 was still 1/2. And then the probability I select a red ball, given that I selected bag 2, would be 2 out of 4, which would be 1/2, which would be 1/4. Right? So it's less likely after I've completed this experiment that I selected bag 2 and a red ball than I selected bag 1 and a red ball. Not because I was less likely to select bag 2, but that once I did that, I was less likely to select a red ball. Okay. So now, the question that we're going to want to answer is, here's a question that we're going to want to answer. We're going to have to take some steps to get there. What is the probability, given I selected the red ball, what is the probability that I drew it from bag 1? Right? Because when I complete this experiment, I pull out a red ball, I look at it, I know I have a red ball, right? But I don't know if I'm holding bag 1 until I open up the bag and I empty the contents out. And then I can figure out whether it was bag 1 or bag 2. Right? I mean, that's ultimately the question I'd like to answer is, I give myself some new information after I'm done. Maybe selecting a red ball is a test that tells me I'm more likely to be in bag 1 than bag 2. It seems like it's saying that, right? But it could be bag 2 and it could be a false positive in some way, right? So it's really just that same sort of idea. And to answer that, we'd say, okay, well, I need to know what's the probability of B1 intersect R. Oh yeah, we've already calculated that. But I also need to know, the denominator, the probability of R. Which would be that question of, okay, I'm going to start this experiment, I'm going to select a bag and I'm going to draw. What is the probability that I draw a red ball out of this experiment at all? And I'll say it's the following. It's the probability I draw bag 1 and the probability I get a red given, not intersect. I drew bag 1, right? That's one way I could draw a red ball. Or I could have drawn bag 2 and then the probability of red given bag 2. Right? I mean, if you think about it, how can I draw a red ball? Either I draw it by getting bag 1 and a red ball, or I get it with bag 2 and a red ball. Right? That's the only two ways I could get a red ball. Does that seem clear? Right? That's the only way that's going to happen. Those two things are distinct. Right? I can't draw from bag 1 and bag 2, right? I mean, those two things are mutually exclusive. They can't happen at the same time. And so I can compute this probability, and I can compute this probability. If there's no bag 3, there's no other way to draw a red ball than to draw it out of one of the two bags that I've selected. And so then I can compute that probability in that way. And so, 2 minutes, we'll finish this off. Right? And so it's saying, well, we've already calculated those two things, right? The probability that I draw a red ball out of this, since these are the only two ways it was going to occur, should be 3/8, drawing bag 1 and then the red ball, plus 1/4, drawing bag 2 and then the red ball, right? Which would be 5/8. At the end of this experiment, the probability of selecting a red ball was 5/8. So now I can answer this question here. because I know the probability of selecting bag 1 and the red ball was 3/8. I figured out the probability of selecting a red ball was 5/8. And so this probability would be 3/5 once I simplify it, 1.6. So if I want to use whether or not I draw a red ball from a bag as a test to say, you know, I think it's bag 1. When I started this, right, think about it this way. If I complete this experiment but I do not look at the ball, right, so I pick up a bag and I pull out a ball and I keep it hidden in my hand, right, and then I ask the question, what's the probability, I've not seen the ball, what's the probability I'm holding bag 1 in my hand? The answer is 1/2, right? Because I don't know anything about this bag other than it was one of 2 bags that I ended up picking up, right, which is 1/2. And then I open up my hand and I see a red ball. Now what's the probability I'm holding bag 1? 0.6. So I've updated my probability, right? So that idea of, right, without the additional information, the probability that I drew bag 1 was 1/2, right? That was what I could call my prior belief, right? Without any additional information, that's what I thought, right? That was the likelihood of that thing happening. These names like prior and posterior are oftentimes used in game theory, but they fit in probability too, because now the only thing I did is I opened up my hand and I looked and I say, there's a red ball. It's allowed me to update that belief, right? I still don't know if I'm holding the red or the blue bag, the bag 1 or bag 2, but now I could at least judge it. I think it's a 60% chance that I'm holding bag 1. Okay? And I could reach in and draw a second ball on it. If it's red again, I'm probably even a little bit more confident there, right? So as I give myself additional information, I can update those beliefs. By the way, this is just an example of what's called Bayes' theorem. And we'll talk about this more on Monday. Right? We'll talk about Bayes' theorem and we'll talk about independence, right? And Bayes' theorem is this idea that as you get more information, how do you update these previous beliefs that you had on it? All right, we'll stop there. I will send out sometime this afternoon around lunchtime some problems with conditional problems.